Hi class, we are now in chapter 26.5. This is bonding and coordination compounds. So bonding takes place when a filled atomic orbital on the ligand overlaps with an empty atomic orbital on the metal ion. What this is called really is coordinate covalent bonding. And what that means with coordinate covalent bond is that the electrons are coming from the ligand into an empty orbital on the metal ion, and that is where the covalent bond comes from. So we're going to look at the geometries of it, but we're not going to go too much into the next section discusses the color and so forth of what's happening here. So this is about the geometry shapes. So hybridization, you learned well prior to this section. Remember, it's when these combine, and then you get the hybrids of it from an S and a P. So you have the sp3, dsp2. We're going to focus on the d orbitals here. 111 and I think 110. You kind of learn about d orbitals, but you really don't focus on them as much. So crystal field theory, this is where this comes from. And to explain it as easy as possible, okay, so the basic premise of crystal field theory, I'm going to try to make this, it's not as difficult as I think some of the books are trying to explain it as. So basically, the premise is that there are attractions between the metal and the ligands, and this has to do with the d orbitals. However, there's also electrons that will be repelled at certain points based on how the geometry and the orbitals and everything is set up for that. Sorry about that. Okay, she stopped barking. So basically, the electrons that come from the ligand are donated into the d orbitals of the metal. However, there is also a repulsion that goes on based on the d orbitals themselves and how the geometry shape is, how it's oriented. So there is also with repulsion, that means higher energy. Chemistry is all about lowest energy. Lowest energy is the most stable of the compounds and so forth. So everything wants to go to lowest energy. However, because of repulsion, that creates a larger energy. So that means that there's an energy difference between that's caused by the repulsion, and that energy difference is the crystal field theory. So we look at the energy differences that are created. Are they large energy differences, or are they small energy differences? And all of this determines what's happening with these compounds. So it basically describes the energy of the d orbitals in the coordination complexes, and the identity of the ligands also determines this difference in energy that happens with these compounds, these complex ions. I should change it to the next slide. So here it is. Here, that's crystal field theory. It is this difference. You see here, this is this little triangle here, this delta. This is the crystal field splitting difference, and you can see the energy difference. So first we start out with degenerate orbitals. Do you remember that fancy word from a long time ago? It means that all of these are the same energy. These orbitals, doesn't matter which one it goes in, they're all the same energy. However, when we start looking at these ligands that are being donated, the d orbitals now change. This is for an octahedral, an example here. Some of the orbitals are lower in energy than the other ones, and there is an energy difference between them, and that's what the crystal field theory is based on. When these are degenerate, this is before anything happens, and then once something happens, this is what it ends up looking like. So now we're going to look at why does it start as degenerate orbitals, and then we have a difference in energy. Some are considered higher energy than the other orbitals. Okay, so when we're looking at a transition metal or a metal ion, where the x, y, and the axes intersect. Well, when a ligand comes in, some of the ligands will actually, such as with the two orbitals, the dz2 and the dx2 minus y2, they're located directly on the axis, and the ligands bond there. But there will also, because it's on, remember we're looking at electron densities, and there is density to the metal ion, these electrons will start repelling where the axes are, and that can cause higher energy. Some of the other orbitals, the three that are listed below, the dxy, dxz, and dyz, are not on the axis themselves. They are between the axes, and because of that, they have lower energy. So when you look here, you can see that why you have two that are higher and two that are lower. Okay, so, and that's what this exactly says here. When the ligands approach, they form a coordinate bond. The coordinate covalent bond is because the electrons that are donated come from the ligand, not the metal ion themselves, into empty orbitals. But the metal ion still has, it does have charge to it. Their electrons repel the d orbitals and causes them to split into two sets. Now, it doesn't say it on this one. There's two energy levels. They're designated EG or T2G. This slide is from another book, and they do talk about it. Your book kind of doesn't even discuss this. This does exist, so I'm putting it in here because it does make it easier to explain the levels. But, yeah. So because DZ2 and the DX2 minus Y2 are located along the metal ligand bond, they are strongly repelled and they increase in energy, and that's why you see this up here. So that means that they would be in the EG, they increase in energy, and that's the EG level, because remember this is saying there's two energy levels. The other three that are located between the axes are lower in energy because they are not directly dealing with the repulsion themselves. So there's a very small increase in energy, and that's the T2G. So let's take a look here. We have the three, and you can see these are directly on the axis themselves. So when the ligand comes in, you see the ligands are actually going right on to the axis, and that causes a repulsion. But these orbitals here are in between all of this, and I think I have a better slide that shows that here. So you can see where the electrons, see the little electrons, they're all on the axis. But the orbitals that are in between where the electrons are located, they're lower in energy, and that is why these have a difference, a lower energy, so there would be a difference in what you see here, why one's higher than the other. And I think that slide's coming up. So this is basically stating exactly what I've said about the weak. There's weak repulsions. This is a very strong repulsion because they are located within where the axis is, and the other nodes are not. So this is the slide. The size of the crystal field splitting, which is delta, depends on the kinds of ligands. I'll be honest, I'm thinking this is delta. It doesn't say anywhere what the actual name is. So crystal field splitting energy is what we're going to call it. Depends on the kinds of ligands and the relative positions on the complex ion, as well as the metal ion and oxidation state. So there's a lot of things. So what type of ligand is it? What type of metal is it? What type of metal ion? What's the oxidation state? How many electrons does it lose? Is it a +2 or a +3? All of this determines the energy difference for these d orbitals. And what we're looking at here is an octahedral complex. Okay, so splitting, this is from another slide, so that's where you see the EG and the T2G. So it will fill, and there's even a certain way it will fill that will cover. So it starts like this, and then it goes to this. And this is the difference in the, it says right here, crystal field splitting energy. All right, so then there's another shape. So we looked at an octahedral shape, but here's a tetrahedral shape. So this is a 4-coordinate coordination compound. So unlike the other one where if you look here, we can see there are 6. 1, 2, 3, 4, 5, 6. Now we're dealing with a 4-coordinate compound. And this complex, the metal between the X, the Y, and the Z axis. So this is in between the axes. So the orbitals that most strongly interact with ligands in a tetrahedral coordination compound are those in the T2G, namely the DXY, the DXZ. I think I have a better slide here. I guess I don't. I thought I had a better slide here. Okay, so these, because remember, these ones are directly on the axis and these are not. So the DXY, the DXZ, and the DYZ, the orbitals with electron densities along the X, Y, and Z axis are repelled to a lesser degree. So now it's flipped. So the result is the tetrahedral complex exhibits d orbital splitting that is opposite of octahedral. So you're going to see what's opposite of what we're looking at here. Because this is where these are on the axis, so they have the electrons are repelling each other, and these are in between. But now we're dealing with the opposite. This is in between the axis, and so these that are directly on the axis are going to be repelled less, so they're lower in energy. So this is the exact opposite of octahedral. Remember, these are also less ligands that are attaching to it, so there's less repulsion. also, there's always less, I lost my place here. So because there's fewer ligands, there's less electron-electron repulsion than would be in the octahedral. There, I said it. Okay, so now we're at square planar, and I just realized now that I've already recorded that they gave me a slide that is incorrect. Please refer to page 1155, I think it is. Excuse me. It is showing the correct. This is, you see, it's for tetrahedral. This is not square planar. And square planar has the most complex of looking. It's like a stack. There's two, and this is, it would be XZ and YZ, and then there's three different levels that stack above each other. So there's different energy differences that look a lot different than this. So we have two here. That one actually has 1, 2, 3, 4. And it shows you differently right here where you can see the electrons are on the axis and not in between. So I didn't realize that that they gave me a slide that is not correct. So please make a notation that this is for tetrahedral and not for square planar. It is in your book. That does show that image. In your book, it's figure 26.18. Okay, so square planar tends to have D8 metal ions, and that would be platinum, palladium, iridium, and gold, and gold 3 plus. So these are, and that's why it says the most complex splitting, because it looks like a high-rise building. It's got more, it goes up this way instead of across the way that these do. Okay, so I apologize for not catching this. I try to catch everything, but it's always when I record or always when I get an exam out that I've noticed a mistake, even though I've checked stuff millions of times. So in a square planar complex, the ligands bond to the metals along the X and Y axis. That means that this DX2, even though this is not the same right one, I'm going to show you the DX2 are most strongly repelled by the ligands. So because they're most strongly repelled, they are the highest above here. So if you think about, there's 2 on the bottom, and then it goes 1, 2, 3. So the DX2 would be the highest energy above because it's most strongly repelled by due to the repulsion. Then, okay, so what it is it's dx2 minus y2, and then we have a dxy, which is the next level, and then a dz2. So the next one is dxy. That's the middle one here. That's the second from the top. And that one has an electron density between the axes, but it is also repelled because of the proximity of the ligand. So it's not as bad as the dxy2, but it's the second most one. The dz2 orbitals have a small amount of electron density within the xy plane, and they are split at a slightly higher energy than the two that are at the bottom. And the two that are at the bottom are dxz and dyz. So these are the lowest in energy, and then the one that's slightly above it is this one, then this one, and this is the highest one. So hopefully I make sense. Please look at a picture when I'm saying this, and then it will definitely make more sense than what I'm trying to say right now. Okay, so not only are they split, we have to look at certain things that happen. So the energy difference between the two, in, for instance, like the octahedral, it gives you a symbol of this delta with a 0, and I know I'm not saying this right, but crystal field splitting and with a little 0. Your book doesn't give this. This is from another slide. When this energy difference is small compared to the energy needed to spin pair two electrons in the same 2Tg orbital, electrons can occupy both the lower energy orbitals and the higher energy orbitals. I'll give explanations to what this is. It may not make sense. This forms a complex with more unpaired d orbitals, which has a high spin configuration because all unpaired electrons have all the same half spin. So what does this mean? So this is high spin complexes is what it's called. High spin complexes, low spin complexes. High spin complexes have, so this has to really do with paired electrons and unpaired electrons, and it has to do with the d orbitals as well as the ligands that are attached. So the energy difference determines if, for instance, electrons can make it even up to a higher energy level, or will they just stay down in pair compared to not being able to get up there. But if the energy, if electrons can get up to the different d orbitals that are higher in energy, they tend to be more unpaired. So that's what this is trying to say. Are they going to be paired or non-paired? That will determine if they're a high spin complex or a low spin complex, if that makes sense. So first we need to talk about ligands, and on page 1153 it discusses ligands, and what it does is it discusses if they are typically strong field ligands or low field ligands. And I just realized they didn't give me a chart of the ligands in this one as well. I apologize for not giving this information, but it is on page 1153. It does show in colors which ones are weak field ligands and strong field ligands. So what does that mean? So let's look at the ligands first. So there's something called the spectrochemical, I lost the name of what this is called. Well, they call it spectrochemical series. And it is a range from ligands that result in a large energy difference to the smallest. So if you look at it, it's on page 1153, and I believe it's going to be brought up in the next section because the ligands help determine what's going on. The different ligands, and if there are typically strong field ligands or low or weak field ligands, basically determine the difference in their ability to split the d orbitals. So that's what it is. What kind of ligands help split the d orbitals, and that means the difference in energy. So ligands that can produce a large crystal field splitting are called strong field ligands, and they are cyanide, NO2 minus, I forgot what, and ammonia. And then we have low field, weak field ligands, which are water, fluorine, or hydroxide, chlorine, and there's a hierarchy for those as well. So if they are strong field, again, ligands that produce large values of crystal field splitting are considered strong field ligands, and this is a large energy difference. And those that give a small value are weak field ligands, are weak field energy difference. They give a small energy difference. So not only does the ligand play a part in it, it's also the metal. If a metal has a higher oxidation state, that also changes the change in the difference in energy of the crystal field splitting. So there's behaviors, it has to do with the metals as well as the ligands. So when we look at spins, high spin and low spin, so complexes with strong field ligands have fewer unpaired electrons. So let me repeat that. Complexes with strong field have fewer unpaired. Why is that? Because the difference in jumping up is too high. So they will stay paired down at the lower energy fields because they can't get up there. Where if they have low spin complexes, they tend to be more unpaired. So if we look here, you can see where if it's lower energy, you get more unpaired because it can jump up into the higher orbitals. But when it's too high, then it's harder to jump up there. So they tend to be paired. So if they has a small energy difference, it is not paired. It's and if it's unpaired, I should say. And if it's too high, then the electrons tend to be paired because it doesn't have enough energy to reach up there. So this just gives you an idea of when you're looking at a D1, D2, D3, D4. Now, some of these in the blue, they have the ability to either be low spin or high spin complexes. So it just depends on, so you can see there's a D, so it's a low spin, it looks like this, and that's because they're all paired. But when it's a high spin, it looks like this because there's a larger, it's unpaired. Is that right? I think I said it that right. Hopefully I said it right. Your book definitely tells you. I'm looking at your book right now, and it says low spin complexes are strong field ligands, have fewer unpaired. Complexes with weak field ligands have same number of unpaired electrons as the free metal ion and are high spin complexes. So I'm not messing that up and getting myself confused. Then it goes into breaking down what a D4, D5, D6. They can have different possibilities, and it just explains that there are 3 lower energy orbitals, and D1, D2, and D3 metal ions always have unpaired electrons independent of the change in energy. So that's what it's showing with here, the D1, D2. So it has nothing to do with energy. That's how these are set for this. D8, D9, and D10 metals. The 3 lower energy orbitals are completely filled. So the remaining electrons fill the 2 higher orbitals, and that's also independent of the change in energy. And here's a slide that's highlighting those points, so D4 to D7. Okay, so write the electron configurations of the d orbitals in the following types of octahedral complexes. So we're looking at octahedral. A low spin D4. So I've given you a lot of the information here, but if it's a low spin, then it says it has fewer unpaired electrons relative to the free metal. So in this case, there's not really much that can be done. It's not going to pair up because it has ability to spread out. So it's going to stay at the bottom. It's not going to stay at the top. And here it is going to spread out. And D4, 4 electrons. High spin has enough energy to get up there. So it's going to now be completely unpaired. Okay, so now we look at a copper complex. I broke this down so you can understand how many electrons we're dealing with, because if we're dealing with the copper 2, you need to know how many electrons that is. So what I did is I wrote out the abbreviated electron configuration. Remember, we do an S1 D10. Why? Because we move one of the electrons here into the D10. But what if you pull 2 out? How many electrons do we need to use? And that's where some of this confusion may be from. So as a review, I pulled this out. So we take always from the S first, and I left it there so you can see the 0. So that was 1 electron, and then we pull 1 electron from the D10. So 2, 4, 6, 8, 9. That's why you see 9 electrons here. So remember, this is how you do this. This is not difficult, but you have to use the S and the D's in order to understand this. Okay, so if we use a copper complex, you can see how this is filled, and really there's not much more that can be done. You can't go past the orbitals of 2 electrons. So this is pretty easy. It just fills itself. There's nothing to do with it. What about a nickel complex? Well, nickel complex we can fill, and the same thing. Look at how I pulled these out so it makes sense how many electrons we have, and you can see that these will go into separate orbitals. Okay, so d orbitals and tetrahedral complexes. This is pretty much stating what I said. This slide should have been on the other side. It's a 4-coordinate coordination. It has to deal with the X, Y, and Z. And oh, you know, maybe it's here. Yes, I have it on the wrong page. I'm sorry. So you can see where I should have moved this up. I'm sorry. I'm such a mess today. So you can see the bottom ones, and no, this is tetrahedral. This is not square planar. So you can see the difference in the energy differences and why some tend to be. It all has to do where the ligands are oriented on the metal ion, and the ones that have the repulsion are where the ligands are, or close to it, proximity, and the ones that tend to not deal with them directly have to be our higher energy. And it is opposite of octahedral. So this is basically what it's saying with that. And then square planar, I think I got it here. Yes. And here it is. Sorry, I didn't realize I moved these out of order. And I've taken other slides from another book, and these slides here some of them are from another book. That's why some of them don't look like they do in your book. And this is one of the things. It doesn't look like it does in your book because I'm taking it from another book. So when I add them, I don't realize that they are too far down in all my slides. But that's okay. See, it's here. So this is the highest energy, next highest energy, and then we start getting to lower, and then the one that is closer to the lowest energy. So you can see the difference in it. And this is the most complex one of when we're looking at splitting the d orbitals, the crystal field theory. Okay, so your book gives you an example of a calculation, and it's kind of random to me, but I'm including it in here. The complex ion, the copper complex ion, is blue in aqueous solution. If you had been in person, you definitely would have seen this because we would have covered. If you had done 110 labs in person, you would have dealt with this blue solution. It's used all the time. Estimate the crystal field splitting energy. So what's the exact value for an ion? So this energy, this E, is equal to the energy for one ion is what it's looking at. So the first thing we want to do is look at the color wheel to determine. We see it's blue. So what is the wavelength? Remember, we only see what is, what's not absorbed. So if we look at blue, what is the opposite to that? And that's the orange light. So is the orange light that is absorbed, since orange is a complementary blue color. So blue isn't absorbed, orange is, and blue is reflected off. So it's not, it's just not absorbed. So estimate the wavelength for this. So we have an orange color wavelength that goes from 580 to 650. And this is in your book. It shows the color wheel in your book. So we want to take the average of it. So we split that difference, and then we can divide it, and we can tell that the average of this wavelength is 615. So now we're going to plug it in using this equation. Remember, we have Planck's constant. C is the speed of light. And we're going to plug in for the wavelength. So we have Planck's constant, the speed of light. And even though we use nanometers, we have to change it back to meters in order to cancel everything out. So this gives it in joules. Joules is our energy. So this is the amount of energy, and it's joules per ion, even though it's not stating that's what it is. it is per ion. So now we want to know kilojoules per mole, not joules per ion. So now they've added the joules per ion, and we can change this for 2 kilojoules per mole. So we add that in. Here is, excuse me, Avogadro's number, and we can use that per ion per mole. Cancel this out. I'm probably not going to ask you anything regarding this. This is so out of what they're talking about. That's kind of one of my little pet peeves when they talk about something to focus on it, and then they throw something else in that's totally random, even though it is related, but then they never talk about it again. So I'm including it, but if I ask something, it's probably going to look almost identical to this. All right, and then here is examples that are also in your book, and what this is asking for is how many unpaired electrons are in this complex. So I included the whole thing instead of breaking it down just so you can see the steps. And again, how would you know the cobalt? Same thing as I showed you in the prior example of how to determine in these boxes, how to determine how many electrons you're dealing with. So that's something you should definitely feel comfortable knowing how to do. Excuse me. It's a D6, and I also included all these D6s of a high spin and low spin, so you should be able to feel fairly comfortable in dealing with what is a high spin, what is a low spin, and determining how that is. So let's look at this example here. Sorry, I'm jumping here. Look at the spectrochemical series. That's the ligands. So is it a strong field ligand or a weak field ligand? Remember, that will determine the energy difference. And this is a fluoride. So it is a weak field ligand. So that means the energy difference is going to be small. That's going to determine if these can jump or not. So now we have to decide if it's a high or low spin. So you draw the electron configuration, and weak field ligands yield high spin configuration. So now we can count the unpaired electrons, and there are 4 unpaired electrons for this. Now the other example, same thing. You're going to go through the same thing, but you can see that the ligands are different. So now we are dealing with strong field ligands, which means the energy is going to be higher. And remember I told you some of them, if they're higher energy levels, they cannot jump up. They're going to tend to be paired because they can't get up here. So with this configuration, they have no unpaired electrons. So crystal field theory describes the splitting. So this is the energy repulsion. That creates the energy difference. And then depending on the ligands, if they're high field or low field, will also determine if they're going to be paired or not. So the energy, basically, it's the splitting of the d orbitals and what causes them to split. The octahedral complexes are split into 3 degenerate T2G orbitals and 2 higher degenerate orbitals. And depending on the crystal field splitting, it's either a low spin or high spin configuration. Tetrahedral complexes are split into 2 degenerate e orbitals and 3 higher orbitals. The crystal field splitting energies of tetrahedral are opposite of octahedral. And remember, we're dealing with less ligands. They tend to be small. So most tetrahedral complexes are high spin. That was on the slide, but I didn't talk about it yet, so I didn't bring it up. But if you go back to that slide, you'll see that it says this. D orbitals, the square planar, are the most complex. They split into 4 different energy levels. And square planar geometries are typically adopted by period 5 and period